and Leiden University. They collect the emails from you. The QR sends you to a questions, a list of, and basically needs you an email. By now, they already have a large number of cosmologists. I think one of the first one, Professor Gendelman, already is in the list, I know. Also people from Universidad of Chile, the group by Gonzalo Palma, also and UV are already in the list. So you are invited to get in contact. Okay, this is the outline of my talk. The idea is to talk basically three straightforward messages. One has to do with the reconstruction program, something I've been working on more than 10 years. The other is on binding lambda CDM, which has been working in a couple of years ago. And also I'd like to show you something I've been working on the last 2 weeks. It's a very new idea. And I end with a discussion. Well, the context, first of all. Basically, the context, the philosophy behind this idea. Dark energy is, by now, just a name. We don't know what is this source that, and basically we understand that dark energy is the cause of the cosmic acceleration. So far, still lambda CDM and the cosmological constant has dark energy is the best model that fits most of the data, but as you have heard during this week, we are increasing evidence that this model is I think, showing some cracks inside of it. And that's the interesting part, that we can follow that signal, that the model seems to be failing in some part. Well, I don't like lambda CDM, basically by the same reason that everyone has talked during this week. Essentially, we don't know what is lambda, and also not only the value, but also this cosmic coincidence, that this is just has been relevant today and never in the past, just today. Why today? So the idea is to assume, as we know, the emergence of this paradigm started with the supernovae. The idea that we need lambda because we have supernovae data that we can fit. And so if the data put us in this uncomfortable position, data should be the one to help us to find a way out from it. So the idea is to focus on the data, what the data tells us about this new component. So one of the approaches is to use this reconstruction program. The idea is to use probe functions, could be the equation of state parameter or the dark energy density parameter as a function of redshift. We assume a form for these functions. We can choose, these are 2 of the many that are in the market. And basically the idea is that this function contains in a special point in parameter space the lambda CDM. For example, in this case of dark energy density, this X function, I haven't defined it, but this is the ratio between dark energy density and redshift Z divided by dark energy today. So essentially today, X redshift 0 is 1. So lambda CDM correspond to an XZ that is constant, independent of redshift, and omega Z should be equal to -1, independent of redshift. That should be the lambda CDM. If data show us something different from that, then is the positive signal of evolution. That two functions are, for example, the equation of state parameter is basically inside or behind an integral that defines the dark energy density, and the dark energy density is in basically the Friedman equation. That is set up for this this study. The problem with the equation of state parameter is that this is behind two integrals from the observational data. For example, usually in type 1a supernovae, the observational data is the apparent magnitude of the supernovae. And the apparent magnitude depends on an integral of E, the Hubble function. And the Hubble function, the omega, is behind another integral. So there are two integrals between the equation of state parameter and the observational data. So at this point, we decided to take an agnostic point of view because we don't know anything about dark energy. Why we bother to assume an equation of state in the first place? So just assume an arbitrary function for x and look for signatures. What kind of signatures can we obtain for this free function from data directly? And once we have that clear, we can use these features and try to look for models that can predict and give us some ideas about this feature. So here I just want to show you a result with one of these possibilities. This is a quadratic parametrization for this dark energy density. In this case, the probe function depends explicitly on two constants that has to be fitted against data. Zm is the maximal redshift, is fixed and depends on the data set we use. And this is the maximal redshift of that data set. This was an idea that the first time I tested was in 2014. The paper appears during 2015, and the origin of that was and I remember the discussion. I don't know, Joel C. was there. Actually, we're working in a very special meeting invented here by people from la Universidad de Bio Bio. Is the Tometazo. It's a kind of a meeting that we work from 9 a.m. to 9 p.m. during several days in a big table, each one of these researchers working very hard side by side. It was fantastic. No talks, and basically during all that sessions, always coffee around, and the discussion can be made anytime, anywhere, and there is a very nice opportunity to do science. And actually this paper came out from a research. I was obtaining some data, and once Joel C. told me something about a new data release from BOSS. I remember he said me, well, there are evidence of a negative dark energy, and that's what we get from the data. So this is the result from 2015. This type 1a supernovae for that time was the loss sample was 500 type 1a supernovae. And what I get from the reconstruction was an evolution for dark energy. This is X, the dark energy density, vertical axis. And from type 1a supernovae, we get easily and easy to see a tendency for this dark energy density to decrease as you increase in redshift. And actually, it can take negative values for a certain redshift on. And that was quite astonishing at that moment. But after the conversation with Joel C. and the evidence from this BAO from BOSS data release 11, I remember, was nice to find And also using gas mass fraction in galaxies was very similar to type 1a supernovae. However, the large redshift data, CMB or BAO, BAO at that time was, at that point, I didn't use the data release 11. This was the old BAO data that was at that time this kind of data was calibrated with CMB, so was not really independent between them. So basically the result was the large redshift data was in agreement with lambda CDM. However, the local one does not. That was very interesting. Well, and from time to time, remember the first paper was 2015, with every sample, type 1a supernovae sample, I tested this. This is something interesting also because, as you know, has a new type 1a supernovae sample came out. Many of this type 1a supernova was already in previous samples, and in each of this release, they produce a new analysis, a new processing for standardization. And the surprising thing is that even with the same data, but different standardization, you get different results. So this is suspicious. Yeah? And so recently in May, I received a visit of an undergraduate student from Duke University in the States, United States, Lily Orcutt. She was an undergraduate student. She wanted to study with me. She was interested in evolution of dark energy, and was also arrived at the time that we came out the data from DESI. That was very nice. And we repeat basically the analysis with this quadratic formula. For type 1a supernova, we use the Pantheon Plus sample, the DESI, the first year data release, and also we add some information from perturbations, the redshift phase distortion data. And that's basically what we get. This is the most important plot of the paper. So again, the dark energy density shows clearly that this is falling as we increase in redshift. This is basically the message. It's not constant. It's there. It's falling. Okay. And well, this is the result with all the data. Is BAO, the DESI new data, type 1a supernovae from the Pantheon Plus, redshift space distortion, and also some scale from CMB. But this is one of the messages I want to show you. This from the Power of Reconstruction program. The other one was more last year, is by studying the lambda CDM model, but using binning for studying how these parameters changing with the with redshift. There are many studies on that. This was a work done with my PhD student, Eric Pasten. And here we use cosmographic analysis. The idea to use something like, people call it a model-independent analysis. And we fit both, basically Q0, the deceleration parameter today. H naught are degenerate with the absolute magnitude in type 1a supernova, so it's marginalized at the end of the day. And there are two ways to bin the data. In spheres, we are increasing the volume for the data and compute for each one of the sections the Q0, and also in layers. So we depend on, we compute a weight in redshift, like an onion shells, and see how they change. And this is the result. Look at the values. Basically, the most interesting thing here are the sign of the parameters. For example, Q0 a very low redshift, the cosmography expansion gives you a very low redshift, very positive values for Q0, positive ones. So there are no acceleration at all if you do this analysis with Pantheon Plus. And also in layers, we have a huge, very noisy data, a low redshift. But if you see this is 0.0, so there are many sections, bins, where this Q0 is actually positive. However, the errors are very big here. So it's not very easy to read it from layers, but from a sphere, it's clear that there is a huge discrepancy between the cosmography and a lambda CDM. The cosmography, of course, is cut until redshift 0.3 because there is no point to extend this the analysis because it's a perturbative expression. And also in that paper, we studied a possible indication of anisotropies. This is not a complete study on anisotropy, as Diego shows using HELPIX. This is just assuming this direction of the CMB dipole and compute from one direction and the north and south hemisphere the best fit value for Q0. And notice that there is especially a very low redshift. The down direction, that is this color, clearly more closer to 0, so, and the other is very negative. So it's not significant, but it clearly is, even considering the errors it's a huge difference compared to what is the evolution for the rest of the, for a larger redshift. This is for, okay. And the new approach, that is completely new, something I've been working in the last 2 weeks, is the idea is the following. This is specialized for type 1a supernovae. You can do it with any other observational data. We have data for the apparent magnitude for the supernovae as a function of redshift. And the cosmology is behind the luminous distance, the luminosity distance. The cosmology is inside this E. And so inside E is the function, the dark energy density function, the X function. So we can invert this equation and get X as a function of the observable. V, in this case, is this expression, and of course, not only depend on the apparent magnitude, but also the derivative of the apparent magnitude. The complicated thing here is to estimate the derivative because we have data points. So the derivatives are hard to be computed. And the only way to do that is, again, do bins of the data. We have a 1700 data points for type 1a supernovae, the Pantheon Plus. For many, there are at least 10 ways to estimate the ideal number of bins to study. Here I show just 2 of them with 13 bins or 22 bins. As you, the logical is logical, of course, if you consider less number of bins, you have a more smooth function. As you increase the number of bins, the data start to show the more noisy, of course. But look at this result, for example, for 13 bins. This is the reconstructed some way, but directly, we are not assuming any form for X. It's just the data, directly from the observable to the dark energy density point. It's except for a very low redshift, that there is a kind of a group of points that are not clearly close to 1, that should be the value. There is a smooth increase of the function until around 1. This is a zoom of this behavior. However, at large redshift, we have a point which is array negative. And probably this point at that redshift is the one that makes that our previous analysis in the reconstruction function push the dark energy density to negative values and to decrease. But without considering this, the last large redshift data, the function seems to be smooth and increasing. Even with 22 bins, this increase seems to be there. As I told you, this is a work in progress. It's very recent result. I just wanted to show you, just to show you that this is something that you can do in a few hours, basically. And so, to summarize the result, basically, we have, I think, now, even with especially with DESI data, now clear evidence that the strong indication that dark energy is evolving. We still don't know what kind of evolution is that. Is it increasing or is basically increase and then decrease, or as the reconstruction program shows, is falling to negative values. We also, I want to strengthen the importance to test the cosmological principle. Is for any data set, I think it's worth to spend some time to focus on, I don't know, bin the data and explore probably dependency with the orientations of the data. I think it's worth to do. And also, as I mentioned, this idea of the inversion method that I think can be, it's promising, because the results I already showed. And that's all. And this is the QR if you want to connect with this community. Well, thank you. Thank you.
Thank you, Professor Victor Cárdenas. Someone has a question?
Thank you. Thank you. ¿Se escucha o no? Hello? Thank you. Thank you, Victor, for your nice talk. It's pretty interesting, the subject. So my question is the following. From where do you gain the inspiration to write the functional form of the dark energy density?
You said this?
For example, yes.
Yeah.
Or, well, that or the, and also the second one, but yeah, X, etc.
Well, I don't know. There are many in the market, actually. I'm just show you one of the I think the ones that I use more times. There are linear ones. There are other cubic even. Usually the idea is to use a prof function that could be enabled to capture some special features. For example, this function enables you to get negative values. For example, if you use CPL for the equation of state parameter, the dark energy density is always positive. So somehow you are forcing the reconstruction to do that. The idea is to be free enough to be able to capture more. But it's true. Once you choose a function, somehow you are restricted to the kind of evolution the prof functions is available. So.
And is there a particular reason to choose that one, for example?
No, essentially it's the usual beyond linear and also the number of free parameters. The idea is not to increase too much the number of parameters because, as you know, if you have more parameters, you can fit anything. So the idea is to keep the number of parameters minimal. That's the idea.
Thank you.
Any other question?
Thanks for the talk. Now, then, we are now living in an accelerated universe or not? At this point.
That's depend on the model you use. Actually, if you know that after the discovery of the Type 1a supernovae, and they add the history, the stories like that. They add cosmological constant because they can fit the data. The Type 1a supernovae was fainter than they expected at that distance. So the only way to explain that was add the cosmological constant. But the year 1 year after that, people use an inhomogeneous model with LTV metric, the Lemaitre-Tolman-Bondi metric, and they fit the data without dark energy. And so if you change the model, you change the box with you that somehow translate the photons you receive in the telescope. And the conclusions are completely different. So in the case of the using a Freeman-Robertson-Walker, if you use a Freeman-Robertson-Walker theory, you are forced to add something else because non-relativistic matter is not enough. But if you use a metric with LTV model, you have to assume that you live in a void, something like that. By now, the void theory is now ruled out for some reason, but at that time was something competitive and was so. Is really accelerating? Depends on the model again. Maybe in 2 years or in a couple months, someone else came up with a new theory, a new model that enabled to interpret the data, and the explanation is different. Who knows?
Thanks.
First of all, thanks for the talk, Professor. So I wanted to ask, in the graph of the deceleration parameter and function of the redshift, in the analysis where you use like spheres, could the positive values be like an artifact created by the amount of data that you have in those redshifts? Like for low redshift, you have a lot of data, and the behavior seems to mimic the amount of data that you have.
You mean the number of data or the redshift?
The number of data that is enclosed under the...
Well, this is clearly something that once we get the Pantheon Plus data, the first thing we do was test it in this way. It was actually the first exercise we do once we get the Pantheon Plus, and we get these values. And then we started doing in different ways, and this is we finally decided to publish the result in this form. But curiously, most of the time that people use the Pantheon Plus data, they don't consider the very low redshift. So for all the data below 0.01, they are not taken into account to test other models. But they are there. And they are actually the data that was calibrated with Cepheids, actually. But it's weird. It's a very weird regime for this data set. That's it.
Thanks.
Thank you. Other question?
I have a couple of questions. One is about the same thing. Like, what's your physical interpretation of this discrepancy between the layers and the spheres? What's the physical meaning of this? How do you understand this?
Well, there are there are many things here. For example, we are fitting the cosmography and the lambda CDM, the flat lambda CDM, the most simple one. Basically, what we are fitting here is omega matter, essentially, yeah. But in the form that relates the Q0. And the idea is in the case of spheres and in comparison with the case of layers, is that there is a cumulative effect here that is clearly makes that in doing this beams with the sphere at certain redshift this reach the usual lambda CDM model, and essentially somehow this tells a more clear story what is happening in the fitting process. Here, because we are doing this in layers, of course this analysis depends on the how many data you add in each beam, and so it's very noisy. You can have many realizations of this layer analysis in this case. This is more clear what's really happening.
I see. And the other question is in the reconstruction, when you use the absolute magnitude, shouldn't you also include parametrization associated to variations in G effective, like effective Newton's constant? In some models, Newton constant. Yes. In some models, when you have like a scalar tensor, you have a modification there.
Yeah.
And so shouldn't you also include it in this model-independent reconstruction?
That's a good idea to do. I think it's possible to do. Yeah.
Thank you. More questions?
Just a quick question. What you mentioned about excluding some data sets is very important, and there is a discussion in the literature. So concerning the DAISY data, there are people claiming that the problematic point is only one. So if you exclude that, then lambda CDM is perfect. So what is your opinion on this discussion?
Yes, again, well, actually with this, once I get to this point, I think we have to be very careful to study each point and separate. I think it seems like some of the results we are obtaining in the past years were driven by single or 2 points. That's point. And with SE is clear. I think it's the Luminous Red Galaxy 1, I think, is one that drives essentially the evidence for that kind of evolution. I think we have to focus on this part, but it's true. It's very important.
Thank you, Manuel. More questions? Yes. Then thank you very much, Professor. Next speaker, Professor Pedro Labraña from University of Bio Bio. Control.
Okay, let's start by thanking the organizer for this wonderful conference. Thank you, Giovanni, also Joelsi, Carlos, and everyone who is involved in this conference. Thank you. Today I'm going to talk something related with this idea of non-singular cosmology. In particular, it's a work made in collaboration with Juan Ortiz, former student of our master program, and also related with this other work in collaboration with Sergio del Campo and Ramón Herrera. También also with Eduardo Gendelman. What is the idea of this talk is this non-singular cosmology, which is related with this more kind of philosophical question: is the universe have a beginning? And try to answer this question from the perspective of cosmology or physics. At this respect, we have the work of Hawking, which basically say that the answer to this question is yes, the universe have a beginning because there are some singular theorem it was developed for Stephen Hawking using the previous idea of Roger Penrose of the singularity in the black hole. And Stephen Hawking note that the similarity within the creation of a black hole by a collapse of a star, if you invert the sign of time, it's kind of the creation of a universe from a singularity. In the more modern context, you want, there has been extend this theorem for the inflationary context, and this is basically the work of Vilenkin, several work. Here I put just two of them. This one with Alan Guth and Borde, and the other one with Borde, which generalized the idea of Hawking. And at the end, what's the Vilenkin argument? Is the following one. They show that basically null and time-like geodesic are in general passing complete in inflationary model, whether or not energy condition hold. The only thing that they need is that the Hubble parameter to be bigger than 0. Then any backward going null or time-like geodesic have a finite affine parameter, which is a signal of the space-time is not geodesically complete, and it's a signal of we have a singularity. So the answer in principle is that the universe have a beginning. But of course, there are models which escape to this conclusion, and these are the model I want to talk about today. This model could be separated in two big groups. One is the cyclic universe or bouncing universe, and the other possibility is the emerging universe. During this week, I have some people talking about bouncing universe. Today, I'm going to talk the other possibility, which is this idea of the emerging universe. The first work in emerging universe is, in the modern context, was done by George Ellis and Roy Martins. Here, well, I can see this. Here, and what is the idea? First, this model escaped the conclusion of the theorem because they don't satisfy the geometrical assumption of this theorem, which is basically the Hubble parameter to be bigger than 0. In the case of the emerging universe scenario, the idea is the following. We assume that the universe always exists, but initially the universe is static, in the so-called Einstein static state. Then something happened, and the universe starts to evolve, arriving to the inflationary period. That is the idea. Try to revival the idea of the Einstein static universe, but not today, before inflation. That is the idea. So in this case, you have the scale factor have this kind of profile if you plot respect to the cosmological time. The scale factor go to a constant value with this infinite state in time. Then in this case, you consider usually that the universe is homogeneous and isotropic, dominated early time by a single minimal coupling scalar field, the inflaton. Normally, you consider that the universe is closed, and then the scalar field is moving by a potential given by something like that, very flat potential. And then you can prove, I'm going to show that when the inflaton is moving in the flat part of the potential, you can find a solution where the scale factor is constant. As you write the equation, the Friedman equation, you have something like that. If you move in this part of the potential, we consider a strictly constant potential, the inflaton field is moving with, let us say, phi dot constant, And if you fine-tune in this way, you can have a static universe where the scale factor is constant. Okay, and the scale factor is constant during, well, whatever you want. But at some moment, you know that the inflaton is going to arrive to this part of the potential, and the equilibrium condition will be broken, and the universe will start to evolve. That is the general idea of this emergent scheme. Oops. You can see that depending on the initial condition, when the inflaton arrives to this part, you can have inflation in this part of the potential, or you can have inflation in this another part of the potential, depending on the value of the phi dot. If you have the slow roll condition here, you can have inflation in this part of the potential, but even if you don't start with a slow roll condition, the inflaton is moving here, pass to this minimum, go there, and start to go down, and you have inflation in this part of the potential. This is called graceful entrance to inflation. In some way, could give the initial condition for a slow roll inflation. So in this way, this idea of the emergent universe is interesting because, in principle, if a cosmological model which doesn't have the initial singularity, also could be give some idea of the initial condition for inflation. So it's an interesting idea to explore. Of course, have some kind of problem. The first one is mentioned here, that you know that the idea of the Einstein that the universe is static have two problems. In the case of Einstein, they try to model the universe today, and you know the universe is not constant, it's expanding. We know it's accelerating, but expanding. And the other problem we have this solution is that the static universe is not stable. You know, it's something that Eddington mentioned to Einstein. The static universe is not stable, again, homogeneous and isotropic perturbation. So in this case, you can have a universe which is static forever to the time if you have this instability. Interesting, this universe could be stable under more physical inhomogeneous perturbation if the fluid have this condition for the zone speed. But definitely, this kind of universe is not stable under an isotropic perturbation, like type Nk9. This is reported in this paper here. So in this way, it's not possible to have a emergent universe scenario because you know that this static regime is not stable. But as the idea is interesting, you can try to solve this problem going away from general relativity or consider other kind of theory. In particular, in our group, we consider Jordan-Van Dijk models and try to study if it's possible to have an emergent universe scenario in this Jordan-Van Dijk model. We found that it's possible. Our first report is here in the paper to the left. And also we can study the more general perturbation, isotropic perturbation in other words. So it's possible to have a emergent universe if you go away from general relativity. We study in this case Jordan-Van Dijk, but there are other models. Also with Eduardo, we study this emergent universe scheme in this theory for scale invariance, the similar what I explained some days ago, Eduardo. In particular, from this kind of work, we found that this potential will have two flat regions, which the value in principle are free. If you consider that in what of this flat region we have a static universe in the context of the emergent universe, the condition that the static universe was be stable under homogeneous and isotropic perturbation make that the second flat part should to be small. So in some way it's a kind of anthropic principle that explains that the cosmological constant today should be small because the universe is not singular. It's a kind of generalization of that. Also, we have explored the possibility of trying to search for some observational evidence of the emergent universe. And in this case, there are some possibility which is related with the primordial perturbation in the inflaton in this model, because, as you know, for the emergent universe, also in some way with the bouncing universe, the Hubble parameter, if you plot the Hubble parameter in function of the cosmological time, you have this kind of profile. So I start with 0 and go up, and then it's constant during inflation. And this period is called superinflation, with the Hubble parameter going to 0 to some constant value. And this has implication to the primordial perturbation, which basically say that the primordial perturbation, they are almost constant during inflation, but during this period of superinflation, the scale, big scale, angular scale are supreme. So, and this feature, in principle, can try to explain the problem that we have with the low multiple, and if you compare with what is the prediction of the lambda CDM and standard inflation, where you have that everything works very good, but very well. But if you load for the very low L, seems to be that the points are a little lower than what is predicted for the model. You know, everything is okay, but here maybe it could be some problem. And you can see that in the case of the emergent universe, if you plot what is predicted for the emergent universe, you see that the very low L could be supreme, could be less than what is predicted for the lambda CDM. So in this way, you can have some kind of signal of this kind of a model. Okay. The topic of the talk is related with what about these instabilities. As I try to convince, the important ingredient is that the static universe should be stable under homogeneous anisotropic perturbation. In the case I showed, they are satisfy this criteria, but Vilenkin some years ago found a new kind of instability, which is a semi-classical quantum gravity effect, which is calculated in this using the Wheeler-DeWitt equation. So you can have a static universe which is classically stable, but could be unstable via this kind of situation, which is described here. Okay. What Vilenkin claims is the following: they use this work here, which is not a emergent universe, but it's a study of a simple harmonic universe. So this is a static universe which makes oscillation around the equilibrium point, where the universe in this example is dominated by a negative cosmological constant. In this case, you can find that you can have a static universe which is stable. But in this case, you can see you can have this static universe, but it's not possible to go from this static universe to an inflationary period. So this model, this toy model, is not exactly an emergent universe. It's a toy model for a static closed universe. But this is the work. This is the arena which use Vilenkin to explore this possibility. And what happened? What is claimed in the work of Vilenkin is the following: if you write the Hamiltonian for this model here, you can arrive at something like that. In this kind of model, we have a baryotropic fluid and a cosmological constant which is negative. This is the crucial point: negative cosmological constant. Then you have only one degrees of freedom, the scale factor. So the Hamiltonian constraint is given by this expression, where A is the scale factor, P is the momentum. The potential here depends only on the scale factor, and is given for this expression. If you plot the potentials, have this kind of feature here, and you can see that classically the Hamiltonian constraint is say H to be 0. So it's easy to note that here is the classical permitted region for the scale factor, and you have this is the equilibrium point, and you can make a small oscillation around this point. You can go, you have a wall here, you have a wall here. This is the classical region, and the other possibility is the scale factor equal to 0 here. They are the classical solution. But Vilenkin say that if you go to the quantum regime, studied by the Wheeler-DeWitt equation, they have another possibility. In this case, this quantum cosmology via the Wheeler-DeWitt equation say that the universe is described by the wave function. In this case, depend only in a scale factor. The conjugate momentum become an operator, and then the Hamiltonian constraint become an operator with act over the wave function. So you have to resolve this kind of thing. In this context, you can see that you can have the possibility of a tunneling of the scale factor from this part to a equal to 0. And the probability of that is given by this expression when you use the WKB method, and where S is given for this integral, which is basically the integral over this hill here. If you make the integral, give this value. So in principle, you can have this static universe which make classical oscillation, but with this quantum effect, the scale factor could be tunneling and going to equal to 0. And this is the stability what Vilenkin say. Also have to mention that Eduardo said to Vilenkin, which also included in this paper, that also the other possibility that you start here with A equal to 0, and the universe creates from nothing to these oscillator universes. Both possibilities. But we're interested in the possibility of the decay of the universe. So you have a universe with a classical and then collapse to A equal to 0. This is the instability point out by Vilenkin. So we studied this kind of instability in several work, one with Sergio del Campo, Ramon Herrera, and Eduardo Gendelman some years ago in the context of the scale invariant theory. We found that this kind of model don't have this problem, because in this case there are some infinite wall for the scale factor, so they have this problem. And what I'm going to discuss in the time I have is what happened with the Jordan-Brandicke theory in this case. This is a little more complicated because the potential depends not only in the scale factor, also depends in the Brandicke field. Jordan-Brandicke theory, we have discussed in the morning maybe about that. Jordan-Brandicke theory is a class model which is a generalization of general relativity, where the effective gravitational coupling evolves with time, or the space even. The strength of this coupling is determined by the scalar field, the so-called Brandicke field, which tends to 1 over g, the inverse of the Newton constant. So the action of the Jordan-Brandicke theory is given by this expression, where in this case we have a matter content given by the scalar field, the inflaton field here. R is the Ricci constant, this momentum is constant, so we include this momentum inside this effective potential which depend on the scale factor and the Jordan-Brandicke field. So basically say that these things should be 0, where the potential is given by this expression. We depend in a scale factor and Brandicke field. If we search for a static solution, this means that the momentum are 0, then the potential should be 0. And the first derivative should be 0 of the potential. This is the static solution. For this kind of potential, if you plot where the potential is 0, here we have the scale factor, here is the inflaton field. In this line, this potential is 0. In particular, the static solution is here, in this point here. Now, if you want to make a small perturbation to try to understand what kind of equilibrium point is this, is it stable or not stable, we have to study the potential, but not directly the potential, because the momentum structure here is not definite positive in principle. We have this main thing here, so I have to be careful. If you plot the potential, have this strain configuration, this here is the equilibrium point. In particular, this is the equilibrium point. This part is positive, the potential is positive, and this part, the potential is region, the potential is negative. And there is the equilibrium point. Okay? We make a small oscillation, then write the scale factor in this way, the Brandicke field in this way, where epsilon and beta are small. And rewrite the Hamiltonian considering this new variable, and we arrive to this Hamiltonian. And you see that, which we can write in this another more compact way. So here is the dependence of the momentum. You can see this is a matrix with a constant matrix, which is not diagonal, and the other part here, which is the potential, is given by this another matrix here. If you search for the frequency of the small oscillation, this is not related with the eigenvalue of Q, but a combination of P and Q, as I'm going to show. Then you can use the Hamilton equation, this one. So you have the derivative with respect to the time of Q is given by this expression. If you take a second derivative, we arrive to this equation. Second derivative, we have this one, we replace this one, we obtain this one. If you see this equation with respect to Q, this looks like just as a kind of harmonic oscillation. So the frequency is related with this product, the product of the Q, which is related with the potential, and P, which is related with the matrix associated with the momentum. We search for the eigenvalue of this matrix, and we obtain the frequency of small oscillation, which are given by this expression here. If you are interested in that the point was an equilibrium point, a center, then we have that inflaton, the Brans-Dicke potential, have to satisfy the following condition which are here. A condition for the second derivative of the Brans-Dicke potential and a condition for the Brans-Dicke parameter. So we obtain, using this Hamiltonian approach, or result of given in this paper. So we have a classical stability under homogeneous and isotropic perturbation. And what about the tunneling? But in this case, we have to consider the Hamiltonian constraint as the Wheeler-DeWitt equation, which basically take the momentum as operator. Then the Hamiltonian constraint transformed in this equation, which acts over the wave function with depend of the scale factor and phi. And we try to see if this kind of, given the potential, and given this structure, if you have the possibility to move from the static universe to a collapse of the universe, then meaning that the scale factor going to 0. For this case, we use the WKB method. So the probability of do that is given by this expression, where in this case the S is given by this integral, which is we have to define some path in the A and phi dependence. Just to see some particular result, we consider two cases where the phi is constant. Only I move in the A direction. So in this case, the integral is given by this expression. And at the end, we're going to consider epsilon going to 0. And we know that in this case, the probability is always vanished. Then you don't have the possibility to collapse the universe to this A0 to A equal to 0. So, but exists the possibility of the collapse of the Brans-Dicke field from phi 0 to phi equal to 0. And this is explored in this another integral here, where we fix the scale factor and move only the Jordan-Brans-Dicke field, where epsilon here is going to be 0 at the end of the calculation. And we know that the probability of this process is given by this expression. If you want this probability to go to 0, we have to consider another condition from the Jordan-Brans-Dicke field, which is basically that the Jordan-Brans-Dicke field, Jordan-Brans-Dicke potential, when the Jordan-Brans-Dicke field is near to 0, is going to C over phi to alpha, where alpha should to be bigger than 3. In this case, we don't, the probability of the collapse of the Jordan-Brans-Dicke field to phi 0 to phi equal to 0 is 0. So in principle, we have that in the Jordan-Brans-Dicke model, we don't have the instability pointed out by Vilenkin of the collapse of the universe, but nevertheless, we see the possibility of another kind of instability. We are at this moment in study, which, you know, we are here. This is the classical equilibrium point, and we have to study if there's some possibility of tunneling to another point of this line. Nevertheless, any of these points doesn't correspond to a collapse of the universe, because it's not when the scale factor going to 0 in this case. We're studying at this moment this possibility on the bend of the potential. Okay, summarize. A couple of things. First, mention that the emergent universes are appealing since they provide a specific example of non-singular, geodesically complete inflationary universe. In principle, they can justify the initial condition for inflation to occur. They can give a natural explanation for some of the anomalies detected in C and B. In particular, in this work, we study the quantum instability of the Einstein regime of the Differential model, and we found that in principle, the kind of model don't have this problem if the Jordan Differential potential assumes some particular condition. Okay, basically this one. Yes, thank you.
Thank you, Professor. Any questions?
Yeah, very good talk. You know, this is very appealing, all this discussion about the emergent universe. However, we need to have a mechanism in order for the infinite time to have an exit. So, in a sense, we want some kind of instability to get out of the emergent universe and then follow the standard procedure of inflation and all the generation perturbations and all this kind of stuff. So the question is the following: how can you obtain this exit from an infinite, static universe? What happens suddenly and it goes out of this state, and then you have the thermal history of the universe?
Yeah, sure. This is actually it depends on the model. In the model that I have been working, I showed here. This is given by the inflaton potential, because the idea is something like that. The idea is that this is the inflaton potential, and the idea this flat part is going to whatever you want to the left. Then the inflaton, when it's moving with this flat part of the potential, you have this equilibrium situation with the scale factor is given by this expression, and everything is static. But at some moment, the inflaton is going to rise to some part of the potential where the potential is just not constant.
But this moment is after infinite time, right?
Yeah. This is one possibility. The other possibility, which I don't discuss here, but it was a work which I have done with Joey Cosio, a former student of master, you have a false vacuum. Instead of this potential, we have a false vacuum, and the universe starts to evolve by a tunneling of the inflaton field. Mm-hmm. This is another possibility. And the possibility with our study with this model is the possibility that we have quantum tunneling of the scale factor to some part of the scale factor start to evolve instead of collapse to equal to zero. This is the possibility we have explored.
Good, thank you.
Thank you, Manuel.
In the Wheeler DeWitt.
Simple question, maybe, about the Hamiltonian in your model, and come from because you are in the mini superspace, working in the mini superspace, or you need to introduce this n for some reason.
Yeah, well, the n is because at the m
in the Hamiltonian
at the m procedure. And in this case, we don't have shift because we are perturbating the closed universe solution. It's not the more general possibility of quantum cosmology. It's just the static solution, which is a closed universe. And for this reason, we take this decomposition with only n, not the shift. Also, it's more simple. But
and after take a value, or?
And at the end is a what's the name? It's a Lagrange multiplier. So.
Yes, but Lagrange multiplier, but take a value after, or for the model, or no?
Normally take one equal to 1.
Okay. Thanks.
Yeah.
Thanks, Andres. Any other questions? I have a question. Usually we have a problem with the definition of the time in these theories. Usually we need a matter field, yes, to define the time. But in this case, you have an scalar field, and you don't have matter.
Yeah, well, the matter is the scalar field.
The scalar field can be, with the scalar field can be possible to define the time, and you don't have the problem with the time?
With this model, we in principle have the problem with time. This Wheeler-DeWitt equation is don't have time, but we can include time if you include, in our opinion, another scalar field moving this flat potential, and make that this scalar field could be some kind of time. And actually, because this is our second idea to work in this, this is a kind of time model with the Wheeler-DeWitt equation is more easy to write. So to explore the idea of time in the emergent universe could be, in our opinion, more easy to and a more general feature. So this kind of model, I explained that I don't have time. But if you include another, maybe another scalar field, you make this scalar field to be the time of the model.
Okay, thank you. Next, the last speaker of the season is Maria Jose Guzman from the University of Tartu. Okay. Presentation.
Okay, so thank you very much to the organizers, to Giovanni for the nice invitation, and also thank you very much for being here in the last talk of the conference, which is supposed also to be like a long talk after lunch, after everything, and it's even harder because I don't know if I can tell, but we were late because there was some pisco sour. So I usually don't have alcohol, but I had to take a pisco sour because the dean was there. So it's even harder to give the talk. This talk is about symmetric teleparallel gravity, the theoretical foundations, the extensions, and the cosmology. And I will introduce my personal motivations for this research, then the teleparallel framework, some starting work on numerical relativity and its connection with symmetric, then the foundations of f of q and cosmology in f of q. So this is the group of the Laboratory of Theoretical Physics. So there is my boss, Laur Jarv, and then some other guys who are doing teleparallel and also particles. And here I am, and as you can see, well, he is from Greece, and this is me from Chile, and we are the only ones smiling. All the others are like serious. Some of them didn't even send a picture. And we have already some series of conferences on the geometric foundations of gravity. So the next one is Geometric Foundations of Gravity 2025. So it will be, we are planning to have like some school 1 week and then the conference. And so you are very welcome there. And we also have like some online transmission if you cannot travel. So my motivations in my current research are first that we have detection of gravitational waves, and strong gravity is highly nonlinear. So we need numerical relativity in the merger, right in the face of the merger of the black holes, in order to be accurately described. And also we have heard a lot about cosmological tensions, and in particular variable dark energy might suggest that something is missing in general relativity. And finally, we have our own theoretical motivations for going beyond general relativity. And one of these motivations is geometry. So as you already saw, I come from Estonia, and the harsh Estonian winter is represented in these pictures. where we have here like a day with minus 25 degrees and like a lot of humidity. You can see these fractals forming. And also here, these pictures I took myself. And it's like quite beautiful, but you can see like in nature, there is geometry. It comes just naturally. But you don't have to go to Estonia to see geometry, because you can also see it like here in Arica. So you just go and walk in the beach, and you can find also geometry here. So yeah, geometry is everywhere. So why not study geometry? Why study the foundations of geometry of space-time? So this is what I'm going to introduce with the teleparallel framework. Well, we have had several talks on this. So you probably already know that there is like curvature, torsion, and non-metricity, which define how the vectors are parallel transport. I will consider that the metric and the connection of spacetime are two separate entities. They don't depend on each other. So I will start with this metric defined in terms of these tetrad fields, and then co-tetrad fields that they have completance relationships. Then I will consider the most general linear connection. This linear connection is not the Levi-Civita. Anything without any hat here is just either the most general connection or the teleparallel connection. It will depend on the context. So the most general linear connection is related to the spin connection with this equation. And in the metric affine framework, this connection is free, but in teleparallelism, it satisfies some conditions. Which conditions? The conditions that we impose on the geometry. So the most general connection has curvature, torsion, and non-metricity that you can find here. And these form 64 components, and they are spread out in these 3 tensors. You can either think of these 3 properties of spacetime that depend on the connection and the metric, or conversely, you can think that the most general connection can be written in terms of 3 pieces, which is, this is the most general that depends on the usual Levi-Civita, where these hats represent Levi-Civita connection. Then you have another piece that is called contortion and depends only on the torsion. And then there is distortion that depends only on the non-metricity. You can either think this or this way. And then you can just easily work with this in the metric affine framework, where everything is the most general thing and complicated. But you can also think what happens if we impose some conditions. So the condition of teleparallelism, where you have some manifold with totally flat 4-dimensional curvature, this condition is satisfied by this connection, where the connection, you just write it in terms of an element of the general linear group in 4 dimensions with real values. And these matrices, you take the connection in this way. Yeah? And this is just 4 times 4 matrices, the most general possible. However, this is when you impose vanishing curvature. If then you want to impose vanishing torsion or vanishing non-metricity, you get more restrictions on the connection. So the metric teleparallelism is obtained when the non-metricity is imposed to be 0, and that's why it's called metric, because you banish the non-metricity, so you have metricity. And in this case, the spin connection depends on some matrices that are elements of the Lorentz group. So you restrict more components. In these 16 components, you banish several of them, and you have some matrix that can be represented as generators of the Lorentz group. Therefore, you have only 6 functions. On the other hand, you can have this connection that banishes torsion, but not non-metricity. And in this case, this connection you can write in terms of these fields that are scalar fields that represent a coordinate transformation from this system of coordinates to this other. In this case, you are left with only 4 functions free in the connection, which is much less functions than the 64 functions that we started with. Okay, so if you banish curvature and non-metricity, you get the metric teleparallel framework. If you banish curvature and torsion, you get the non-metricity framework. Sorry, the symmetric teleparallel framework. And then now, in these geometric frameworks, you can build theories of gravity. And we have already heard this teleparallel equivalent of general relativity, where everything you have is a torsion. You build a scalar, and you build a Lagrangian. Yeah? And there is this debate in the literature. It was very spicy debate. So there was something called the covariant formulation of teleparallel gravity. And this covariant formulation means that we are going to perform a simultaneous Lorentz transformation on the tetrad and the spin connection. This transformation doesn't change the Lagrangian, doesn't change the equations of motion, doesn't change anything. It's totally harmless, doesn't involve any propagating degrees of freedom, it's pure gauge. However, this teleparallel equivalent enjoys a special symmetry, an extra enhanced symmetry, which is Lorentz transformations only on the tetrad or Lorentz transformation only on the connection. Yeah? So this, we have had this paper published in 2022 where we call this symmetry like Lorentz symmetry of the first kind. No, I think this one is the Lorentz symmetry of the first kind, and this is Lorentz symmetry of the second kind. So when this covariant teleparallel gravity was postulated, they said, oh, we have solved the problem of Lorentz invariance in f of t. However, since teleparallel equivalent has this special symmetry, it means that when you postulate these f of t gravities, this is the symmetry that is broken. So with the covariant version, you didn't solve this problem, you still have it, because these transformations are allowed in teleparallel equivalent, and once you define the nonlinear function of this, then you will always get this violation of Lorentz symmetry, which occurs because the teleparallel equivalent Lagrangian is altered by a boundary term. When you make this transformation, you get a boundary term. And then this boundary term is integrated out from the Lagrangian and from the action. But when you make the nonlinear modification, then it causes lots of troubles. Something similar happens with with this symmetric teleparallel. So now we are working in the framework where curvature is 0, torsion is 0, and the only thing we have is non-metricity. And we build this non-metricity scalar, and now all the connections that you will see without the hat, they will be connections that do not vanish the non-metricity, but vanish curvature and torsion. So you build this scalar, you see that it differs from the Ricci scalar up to a boundary term, and then this boundary term is sensitive to diffeomorphism transformations on the metric. Yeah? However, you have some sort of covariant version of symmetric teleparallel, because you can define simultaneous diffeomorphisms in the metric, and the connection leave the theory invariant. So this is like the most general gauge symmetry of the theory, which doesn't alter anything, doesn't have dynamics, anything. But in the same way that teleparallel equivalent has this Lorentz transformation on the tetrad that gives you a boundary term, symmetric teleparallel also has the same property. Well, and you can see it here. Every time you make some coordinate transformation only on the metric, you get some boundary term that gets violated when you take the f of q theory. So one more remark is that in teleparallel equivalent, you can always make a Lorentz transformation that leaves this connection 0, but you will have some Lorentz rotated tetrad there. So the choice that you banish this omega is called the Weizenbock connection. Yeah. In the same way, in symmetric teleparallel, you can take some coordinate transformation. here. Where do I have, no, the connection, I had it here. You can take a coordinate transformation where these scalars are exactly these coordinates. When that happens, the connection trivially vanishes, and that's called the coincident gauge, which is what I call here the coincident gauge. So this scalar, here this nometricity has some connection, arbitrary connection. If you take this special set of coordinates where the connection vanishes, then this Q just is the partial derivative of the metric, and then what you obtain is that the nometricity scalar is just the gamma-gamma part of the Einstein-Hilbert Lagrangian. So in principle, the coincident gauge is just general relativity without these derivatives of the connection, right? And this action has been actually studied even by Einstein, I think, and Dirac did the Hamiltonian formulation of this, and the paper is like really, really complicated. He did it in a very complicated way. And yeah, so when people talk about the coincident gauge, it's just this gamma-gamma action. So that's why I actually don't think it's interesting to study the coincident gauge. I think it's interesting when you leave the connection free. But as you can see from here, the connection has second-order derivatives in these fields. So actually, if you consider this as the fundamental field, then the equations of motion will be fourth order, and you will have lots of troubles. But there are some ways where you know, we can define these like some sort of like auxiliary tetrads, and then you will only get first-order derivatives in this auxiliary tetrad. And now, yeah, so because of these boundary terms don't affect like the essence, the kinetic part of the equations of motion, but they could alter, like for instance, things that happen in the boundary of on the manifold, like black hole thermodynamics, and actually also the equations in numerical relativity. That's what we are doing research now. And I want to maybe convince you that, oh, it appears very small. I maybe want to convince you that there is actually some change in the equations, and for that we have to go like to the Hamiltonian formalism. But first, we will think about the ADM split of the symmetric teleparallel. So what we have to do is the 3+1 split of the gamma-gamma action, which is just even less work than for general relativity, because you don't have to do the ADM split of the d-gamma part. However, the expression looks more complicated. So, well, it looks very tiny here, but this is something that is like the three-dimensional part of the nometricity scalar. This is the extrinsic curvature, and these terms, they exist in general relativity. They appear, you can find in any book. But then there is a bunch of other terms, and in particular, the terms that are most, you know, problematic or controversial are those that have time derivatives on the lapse, and time derivative on the shift. So now the question is, do you think that this is like a problem? Well, the answer is no, because they are just linear in the time derivatives. So once you define the Hamiltonian, they will just be removed. But we still have a bunch of other terms. And what happens that all these terms, after some work, you can find that they are boundary terms, actually. Yeah. However, you can make this process of integration of boundary terms infinite times. So the question is, which boundary term will we take, right? I can define the, I mean, every boundary term will define like some different Hamiltonian, different momenta, etc. So I could think, you know, computing Hamilton's equations from one Hamiltonian, another Hamiltonian, and what I will get will be like something different. So, and also one important remark is that these boundary terms here, they are not necessarily the same as the Gibbons-Hawking-York boundary term. And there was actually also a lot of confusion in the literature. They thought like, because the torsion scalar differs from the Ricci by a boundary term, then this boundary term must be the Gibbs-Hawking-York boundary term. But actually, they are not the same. And what you will need to prove, which I think it's in some paper, but I don't know if the proof is rigorous, that you have to prove like the variation of this boundary term. It gives you a well-defined variational principle. The problem in teleparallel equivalent is that you have to make variations on the tetrad. And that is like, more complicated because you have to relate the variations of the tetrad with the variations of the metric, and then the boundary conditions on the metric, you have to project them on the variations of the tetrad, and that's not simple for some geometries. So this form of the 3+1 split of the symmetric teleparallel equivalent action, it was presented in this paper in 2020. But actually, this discussion that I'm telling you, that without making any integration by parts, you have these time derivatives of lapse and shift. This was discussed in this nice paper that one of our PhD students found, actually. And it's very well, it is nicely discussed because they show even the primary constraints. They show that the primary constraints associated with this unintegrated boundary term, they differ from general relativity, obviously. So actually, there is some change in the symplectic structure, let's say. And also in this paper, as I will show later, they integrate out these boundary terms, and then they obtain something that actually is general relativity. So this is general relativity, and then this stuff might look like different, but you can prove actually that these terms are the three-dimensional Ricci scalar. And then you just find the 3+1 split of general relativity. And the thing is that in this paper they show like all the Hamiltonian formalism of this theory, which is supposed to be symmetric teleparallel, but actually it's just general relativity. And that's fun. I think the paper never got published because probably it didn't have new things. It was just the Hamiltonian formalism of general relativity in another fancy language. So that's why one of the ideas, one paper that I also put last year and actually still not published, is that we can take any, we can take more the essence of the symmetric teleparallel, and this essence, actually, of all the teleparallel models, is that here, the torsion depends on first-order derivatives of the tetrad. And here, the non-metricity depends also on first order of them on the metric. So there are no second-order derivatives. And I mean, if you ignore these boundary terms, then it turns out they are like suitable background for building, maybe, a suitable background for building modified gravities, because the equations of motion will always be second order, yeah? And then I thought, this 3+1 split has second order derivatives here. Here there are like second order derivatives of the field variables. But if I make some integration by parts here, like I pass this derivative to the lapse, then I don't have second order derivatives. I just have first order derivatives. And that's more on the spirit of symmetric teleparallel. And that's why I just had the crazy idea of studying like the, the 3+1 split with this choice, and then find the Hamiltonian constraint, and soon I will also show the Hamilton's equations, which actually change the definitions of the canonical momenta, and actually Hamilton's equation also change, but not in the kinetic part, just in the, we could say like in the gauge sector, yeah? I haven't proved that this term has a well-defined variational principle, so that's work in progress. And however, that's why people, actually, I'm not the only person who says that this teleparallel formalism can give something new in numerical relativity, but I just thought like the papers in the literature are not very clear on this, so I decided also to to take, to put the hands there and compute some stuff. So this is the interesting thing, that is just the equivalent of general relativity, and you already find something kind of different that you could take advantage from. Another probably more straightforward way of studying these boundary terms is black hole thermodynamics. And that's been done by the students of Tommy Koivisto. And the interesting thing is that these boundary terms, they have the connection. So apparently the connection, which seems like a dumb variable because it's just like some gauge there, it actually can play some role in like black hole thermodynamics. And that's also interesting. Now, as I told you, well, we have this, because we have 3 different geometric components, curvature, torsion, and non-metricity, people have called it like the geometric trinity of gravity. But actually, if you consider torsion and non-metricity, then you have like a spectrum of geometry. It's not just like 3 things, but you can also mix them. These boundary terms could have a role on numerical relativity and black holes, and the boundary terms in principle are infinite because you can make just uncontrolled integration by parts, but not all of these terms might have well-defined variational principle. So, this is the first part of the talk. I hope they're not sleeping. Now, the foundations of f of q. I think I will go fast here because we have had some talks. So I talk a lot about this symmetric teleparallel. There is this boundary term that is it doesn't have invariance under diffeomorphisms. I mean, like the q, if you make a diffeomorphism, then you get a boundary term. For the linear theory, doesn't make any change. But if you make this nonlinear modification, then you get problems. So the equations of motion of this f of q look like this. I think they were shown by Manos. And you can rewrite them as this Einstein tensor coupled with this derivative of the f, then this term that resembles a cosmological constant, and the new thing of the theory is here. You see that it depends on this tensor that depends on complicated combination of the non-metricity tensor and the derivative of the q. And in f of q, there is an additional equation, which is the connection equation. And actually, this connection equation is what you obtain from the action when you vary with respect to the connection. This equation is not an independent equation. It can be derived from these equations of motion, assuming that there is conservation of the energy momentum tensor. Yeah, that's it. But still, whenever you want to solve these equations, it is better if you also check this equation, because if you just take any connection that you want and you don't care about symmetries, for instance, then this might not be 0. And then you will know that you are not solving the equations of motion. Yeah. Another remarks on the equations of motion is that there is effective gravitational constant that, for instance, you can just pass dividing this term here. It changes the gravitational constant, and this term has to be positive. So we have this imposition on the f. And we also expect that this variable cosmological constant is, is not 0, but also not infinity. And also, this derivative of this term has to be positive, and this imposes other conditions. And finally, you see that in the same way as in f of r or f of t, if you have a constant, the constant scalar, the equations are equivalent to Einstein's equations, but with a rescale Newton's constant and cosmological constant. So this is not only from f of q, but from all these theories. And finally, the degrees of, well, not finally, like from the foundations of f of q, I talk about the degrees of freedom. So this discussion on the degrees of freedom doesn't come without controversy. Like we have the case in f of t gravity, where actually we still don't know how many degrees of freedom the theory has. Apparently the theory has from 1 to 3 more degrees of freedom than general relativity. And what are these degrees of freedom? You might think that they can be found like at the level of cosmological perturbations or perturbations of Minkowski, but at least at the level of cosmological perturbations, they just don't appear. So on the one hand, you have this Hamiltonian formulation that tells you that there might be more degrees of freedom, but then you don't find them at the level of perturbations. So this has motivated some authors to say that the theory has a strong coupling problem. The problem with the strong coupling problem is that you need to choose a background to make the perturbations, right? So on the first hand, you need that your Hamiltonian analysis doesn't depend on the background. On the second hand, you need like your cosmological perturbations appears always the same with whatever background you want. The problem is that the theory, the Hamiltonian analysis, depends on the background. You get jumping degrees of freedom because it depends, it's background dependent. And the other hand, the cosmological perturbations have not been done in any background, just one specific background. And this depends because the theory is defined in terms of the tetrad, and because the constraints in the theory have nonlinearities because it's written in terms of the tetrad, so lots of headaches. In f of q, people thought maybe it's nicer because we are writing in terms of the metric, but actually, no, it's not nicer because of these laws of diffeomorphism invariance. And there are, up to now, 3 works on the Hamiltonian formulation. The number of degrees of freedom range from 6 to 8. People, like the people who are like well known in the field says that the theory has 7 degrees of freedom. Although there is no Hamiltonian analysis that proves their claims, they say that they have found at the level of cosmological perturbations and because of symmetry arguments. I think it's not clear how many degrees of freedom are, but probably calls my attention that there is one of these researchers that the Dirac-Verman algorithm is not finished because there are failures in the algorithm due to the appearance of differential equations for Lagrange multipliers. So I think it's also kind of strange because there are some examples, like if you write electromagnetism in light cone coordinates, you find actually differential equations for Lagrange multipliers. And actually, in the Hamiltonian formulation of f of t gravity, there are also equations for Lagrange multipliers. So probably what has the failure is the theory, not the algorithm. So that's also some discussion, unclosed discussion. And one can see these problems of the theory if we write the action in the so-called Einstein frame. So if f of r gravity, for instance, you want to, you first write in the Jordan frame where the f, the derivative of the f is a scalar field, and then the action is written like scalar field times the Ricci plus other stuff. Then you make a conformal transformation to remove the phi from the r, and you are just left with r plus a scalar field. If one tries to make this trick with f of q gravity, you actually cannot decouple the scalar field from the metric. There is this extra term where here there is derivative of scalar field, and this derivative is coupled with the covariant derivative of the conformal metric. And this term is coupled with this term, which is not diffeomorphism invariant. So there are like lots of trouble. First, the kinetic term doesn't have the correct sign, and the scalar field couples to the derivatives of the metric. And actually here, it appears the time derivatives of the Lapsan shift, and this breaks the diffeomorphism invariance and produces like some really non-trivial constraint algebra that we don't even know if it closes, actually. Yeah, so I will say it's very important, this analysis on degrees of freedom. And actually, as Manos Saridakis was saying, like, how do we distinguish these 100 theories of gravity? Obviously, observations is the first clue, but then theoretical consistency too. And I wish we had some method for computing this. Every time someone comes with a new theory of gravity, I wish we had like some, machine that we could find out how many degrees of freedom the theory has, or how it is well behaved or not. Does it have pathologies or not? And then probably life will be simpler. And now cosmology in f of q. There is, here you cannot see anything. But if we try to solve f of q equations of motion with the traditional Friedman-Lemaitre-Robinson-Walker metric, we require that the connection is non-zero. And actually, what we find is that there are 3 different connections that are associated with the same metric that solve the equations of motion. So, okay, it's like we have one metric has 3 different connections, and then you write Friedman equations, and they have different dynamics. So it's like from one theory, I have 3 different possible cosmological evolutions, and then I can choose the function f, and then I will have different stuff. But, and well, here you see like the connection is like a matrix of matrices. So here the blue is, like, you have to imagine that the 3 connections are the blue, the green, and the red. And the important point is that there is one function, this gamma of t, which is an extra function that is parameterized in the connection. And we would like to know if the connection has some role in the cosmology. Yeah? So I will call connection set 1 the blue, connection set 2 the green, and connection set 3 the red. So in the last slides, I will be working with the blue and the green, which are connections set 1 and 2. What we try to do, well, here, yeah, now I'm showing you the Friedman equations for connection set 1. No-metricity scalar is the same as the Ricci scalar in traditional cosmology. The equations of motion I have put here in blue the contribution from the modified gravity, and the black is general relativity. I'm also showing here like that we can write the system like this, the derivative of the Hubble parameter in terms of things that don't have derivative, and the derivative of the density, matter, radiation, cosmological constant, in terms also of the variables without time derivative. And what I'm showing here is that we can, depending on the function f, we can find a singularity where h dot diverges. And that will also happen in connection set 2, where I'm showing the equations here. So you see, we have 3 equations. This 6a squared, h dot, blah, 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 and then continuity equation.
So Maria Jose, in this H1, gamma does not appear.
No. But in connection set 2, now we have the gamma, yeah. So, now we have the connection here in the cosmology. What's going to happen? We don't know yet. But there is also something, I have 1, 2, 3, 4 equations. What is this equation, right? It didn't appear in the previous connection. So this equation is the connection equation, actually. And you can prove that this equation depends on the previous ones. It's like you take one equation, take the derivative, mix with the other, and you obtain this connection equation. So for our analysis, we didn't use this equation. Yeah? So now, I have 2 sets of different cosmologies. One of them has the connection here, the other doesn't. And the analysis we did with Laur Yarv and Lakshmi Priya Pati was to study the stability around general relativity. So we didn't move to cosmological perturbations immediately. What we wanted to know is if this set of cosmologies reproduce like the eras of the universe, radiation, matter, cosmological constant, and if these eras are stable or not. So we implemented this method for studying the dynamic stability of these eras around general relativity. And if you see, like, the equations have general relativity plus non-general relativity, and we know how general relativity works. And we want to find the function f such that the non-general relativity part is 0. And for the two different connections, we found some conditions for the f so that the non-general relativity part vanishes at the background level. And then after we check that actually they can be banished for some reasonable function, we perform perturbations on the nometricity scalar, the Hubble parameter, the function gamma of the connection, and in whatever matter we are considering. And these perturbations, Q, H, G, and R, we consider small perturbations of approximately the same order, and we proceed to perturb the equations. And here I just show the results. For the connection set 1, in the radiation era, we find that these perturbations decay with time, in matter also. And here, some words need to be said about dark energy and geometric dark energy, because in the dark energy era, we put some cosmological constant there, and we let the geometry do its thing. In the geometric dark energy era, we don't put cosmological constant, and we let the gravity to do the role of this variable cosmological constant. For both of these options, well, here the perturbations go like constants, so this could be considered like marginally stable, and these perturbations decay, so they are like stable. So at least for connection set 1, we think that this geometric modification can satisfy the role of the cosmological constant, and it has stable perturbations. However, for connection set 2, things are a bit different. Well, perturbations for radiation and baryonic matter, they decay with time. Well, except here, where we have some marginally stable regime for this perturbation of the function of the connection. And then cosmological constant era is marginally stable, and geometric dark energy era is decays with time. So, and also, as I showed you at the beginning, the H dot had some points where it can explode, yeah? Like the denominator can be 0 for certain functions, and you can have a singularity in cosmology at the background level. What we did here is like we choose some particular function with some numbers, and we plot how how the gamma behaves. And we took some numerical values, a little bit up and a little bit down from this evolution. And what we show with this numerical example is that the gamma can, well, actually the H dot goes to explodes, and the H goes to 0 in a finite time. So in this point, the gamma is 0, and a singularity is reached in the H dot. And this shows that this is not very good, because there is no physical mechanism in the cosmology that prevents us from hitting a singularity. And that's really bad. It happens in connection set 2. So the conclusions of this is that I'm not showing everything, sorry. But they have 3 other plots. It's in H dot, and H dot exploding is reached when gamma is equal to 0. And it's shown here. Yeah, sorry, because of time, I'm not showing all the plots, but we have like 4 plots in the paper, and it's much better explained than what I'm explaining now. So Yeah, and this happens for some reasonable function and reasonable parameters, and we took the initial conditions from actually the matter-dominated solution that match general relativity, so it's like the most innocent cosmological thing that hits a singularity. Yeah, so the thing is that we find like we're hitting a singularity at the background level. And there is, as I told you, there is all this discussion on cosmological perturbations that, particularly in this paper by, well, Coy Visto, Jose Beltran, and Deborah Aguiar Gomez, where they, and Alejandro, yeah, where they claim that there are ghosts in the theory, and in particular in connection set 2. And the question is that if you find singularities at the background level, it's not of great consequence to find a ghost in the metric perturbations because the background is already pathological. Yeah? We think that we need to study more these background solutions in cosmology because actually what I show you here, like these 3 connections with just one metric, this connection is obtained from assuming certain symmetries in the connection, yeah, cosmological symmetry. But the connection actually is not supposed, I mean, it's debatable if you have to impose like any condition on the connection because it's just some gauge field. So there is also some ongoing research with a student where we want to find actually other backgrounds, and maybe other backgrounds, other cosmological backgrounds in the theory, because they are acceptable by the theory. Maybe they don't have these singularities, yeah? And yeah, and in general terms, the stability of the theory depends on the connection and the particular class of models, because maybe for some Fs, you don't hit the singularities, yeah? And they have to be studied together, and although these studies of ghosts in the literature are important, studying the background is even more important. So thank you very much for your attention.
Thank you, Maria Jose. The very nice talk. Any questions?
So Maria Jose, thanks for the talk. So in your background equations you show around 37, 38. So you have the energy momentum conservation, the typical, the last, yeah, no. Equation 38.
38.
Yes.
Yes.
So 38D, yeah. So do you have to force to us to? So it appears naturally in the structure of the theory, the conservation of the energy momentum, or do you have to assume that?
You have the connection that you couple matter with is the Levi-Civita connection, so in principle the energy momentum tensor just is conserved the traditional way. So it's like you don't have to impose this equation. It's there because in order to obtain the equations of motion, you assume that the covariant derivative of the energy momentum tensor is 0. And then that doesn't have the teleparallel connection. It has the traditional one. Yeah, but it's a good question. Because yeah, sometimes there is confusion, like if you are taking some connection, different connection than the Levi-Civita, then how do we couple matter? The answer is that we just couple matter to the Levi-Civita. But it's a big question, how do we couple matter with these new connections?
Okay, Professor, thank you for your talk. My question is basically related to the considering gauge, because basically what you said is that the connection depends on that choice of gauge, but at the end you mentioned also that we have to take account some symmetries. What type of symmetries do we have to take into account?
It's like if you take cosmological symmetry, then there are the Killing vectors associated with homogeneity and isotropy, and what some of my colleagues did to obtain these connections is that you impose like the Lie derivative of the connection along the Killing vectors is also 0. In principle, it's not mandatory to do it, but it's nice because it gives you simple connections. But what I argue is, maybe I'm wrong, that you don't necessarily have to impose them. Actually, because these theories are so strange that they violate diffeomorphism invariance, there is some review by Lavinia in f of q where there is some debate in the black hole solutions in f of q. Like, if you impose this symmetry, you know, the Killing vectors of Schwarzschild on the connection, then you don't solve the equations of motion, actually. And then you have to take more intricate, like, connections. So I think it maybe deserves some research, but maybe I'm wrong.
Okay, thank you.
Thanks, Maria Jose, for the talk. Very interesting. I just wondered about the numerical relativity part. So you talked about using this kind of parallel language. Well, it was this other paper where they arrived at the 3+1 split. But then the actual implementation of those equations, there's more involved usually in order to get well-posed, like a well-posed numerical problem and something that's hyperbolic and all that kind of thing. Did they study that, or is that something that's known, that is that kind of, that works as well in that formalism, or
that's
you have to?
Future work.
Okay, okay. Right.
But yeah, that's the thing I'm interested the most,
Sure.
like in making some. Maybe there, you know, it would be really nice to have like some numerical relativity equations that they're already strongly hyperbolic. For instance, you don't have to go to the BSSN formulation, and. But I mean, it's a complicated problem. So it's like I need a PhD student, and they don't want to give me yet a PhD student, you know. Okay. So I'm a bit angry there, but it's very interesting.
Okay.
But maybe it doesn't help at all.
Sure.
But I just would like to show it. Yeah.
Thank you. Any other question?
Very nice talk. I enjoyed it a lot. I have a very naive question. Does this theory contain general relativity as f of r?
Yes, it has the general relativity limit.
Okay.
I think you can show from the general equations and also in cosmology. Like, if actually with a student, I was finding these strange cosmological solutions. And if you relax the connection, actually some equations, some solutions don't have the general relativity limit. And that's really weird.
And yes, and is this GR solution far from the singularity, or?
It's like you find this, you know, you have here the general relativity limit, and if you put conditions on this f, then you can make it like, you know, really small, and it's like you can have a lot to play yet thing here. But that's a good question. Yeah.
Thank you very much.
Thank you.
Yeah, very good. Just one comment and two questions. The first is that if the singularity of h dot is in the future, then potentially it's not a problem, because this is the big grip cosmologies. I mean, it's not, okay, it will be a problem for us, but for the theory it's not a problem if the universe suddenly reaches a singularity. Now, my question is the following. Since you have this issue in second connection, why you don't claim that, okay, then I don't accept the second connection and I remain with a connection set 1? Why you don't claim that?
Well, actually, we say in the paper, like, connection set 1 is more preferable. The problem is that maybe we wanted to find some role of the connection, and in connection set 1 is actually the same as f of t, for instance. Exactly. So nothing new there, and why don't we just study f of t?
I guess at the background level, right?
Yeah, the background.
Will it be the same at the perturbative level?
No, because the equations are
exactly.
different.
So it's already. And a more general question, just to hear your comment. You know, there is a discussion whether connections are measurable. and there is a consensus that at a classical level you cannot measure the connection, only at the quantum level with the Bohm-Maharonov effect and all this kind of stuff. So my question is there a possibility to measure an effect of the connection? So for instance, in classical gravity, you cannot say we are living in Leavitt-Civita connection or in Weisbach connection. There is no any observable that you can find, I can explain you with both connections. So here, is there an effect of the connection in some observables?
Is there? That's the interesting thing.
No, I know. Of course, this is what I'm asking, and I like that. But I mean, so can you measure something, and you can say, okay, yes, I measure gamma?
Well, it's hidden here in the non-general relativity part. For instance, if you have some cosmological constant here, well, the gamma contributes to it, non-trivially, unfortunately. It's not like something very nice that is just some term there that only depends on the gamma. I think, yeah, I don't think we understand very well how to obtain the physics of this connection.
I will ask you later on, because we don't have time, because now, you see, in 38C, you have a third derivative of gamma, so how you solve this question?
Well, this equation depends on the others. So all the dynamics here is hidden in the other two equations. So you have to probably do some other rearranging of the equations if you just want to see the evolution of this gamma. Yeah, but actually we don't understand how, like Tommy Koivisto thinks that in the black hole thermodynamics or in the definition of the energy, the connection can contribute. Some others are not very happy with this. So there is still debate, you know. But I think it's interesting.
Other question?
Thank you, Maria Jose, for your nice talk. So my question is, today, are we living in the cosmological constant era or the geometric dark energy era?
Oh, that's a philosophical question. What do you say, Susanna? How do we distinguish it? Yeah, I think we need to live, I don't know, a million years more to see if it evolves or not, you know.
Yeah. So as a follow-up question, the dark tampoco. The geometric dark energy, in the geometric dark energy era, how does the universe behave? Like an accelerating universe also?
Well, it better do the thing that we experience. Otherwise, I mean, you have lots of parameters to fix there. So in principle, if you want like a big rip, you could probably obtain it. If you want, you know, some other bouncing universe, probably you can also get it. It's just like so many parameters. So here we were interested in the stability around the general relativity limit. So we still found like in some cases it's marginally stable. So yeah.
Thank you.
Thank you.
Thank you. Other question? I have a question. This theory is local Lorentz invariance, or?
Yes, because it depends on, it's written in terms of the metric. Okay. So there is no tetrad there that, you know, violates Lorentz invariance. Although, you know, as I show, like this connection can be written either in second order derivatives of these scalar fields, or you can define some sort of tetrad there. Maybe in this tetrad there is something, like you could reinterpret this diffeomorphism invariance, like breaking of diffeomorphism invariance, maybe like some Lorentz breaking on this auxiliary tetrad. I think, yeah. And then maybe it can be interpreted like that.
But I was remembering about the field equation. The field equation seems not be explicitly symmetric.
Yes, they are.
Yes, I'm not sure. For example, the second term?
I think this P, you see, like there is G mu nu. I mean, this is the Einstein, symmetric Einstein, symmetric energy momentum, symmetric metric, and then this term is left. But as I show here, I think you can prove that it's symmetric in mu nu.
Yes, but you know explicitly symmetric.
You don't see it from here, but I think it can be proven. And
okay.
if it's not symmetric, maybe I had a
Yes,
typo.
yes, the last term is symmetric in the first term after the parentheses, but the two second also. The second and the third also are symmetric, but the first seems to be not symmetric.
Yeah, this is symmetric, this is symmetric, this is symmetric.
Okay, the first is symmetric also.
This is also symmetric, and then this other
Yes,
stuff.
this is symmetric.
Yes, actually.
No, oh, this is a strange. No, it's symmetric, yes. But the first is symmetric also, the Q? The Q?
Yeah, because this is non-metricity.
Okay.
And it's it's symmetric in the last two indices.
Is symmetric? Okay.
Yeah.
Okay. Okay, thank you. Then we finish our Congress. Thank you very much. I would like to be honest with you. I have not prepared any words, yes, but I would like to say to you, this event has been very nice, very great, because of you. Yeah? Your participation, your contribution allow us to have this excellent Congress. Yes, and then congratulations for all of you. Now I would like to call the other members of the organizing committee, the Professor Joel C. Leiva, the students. Yes. Any other word? Any other word? Okay.
Well, I would like to express our acknowledgement to all of you for coming to join us in this meeting. We send the invitation all of you, if you answer enthusiastically to come to Arica. These 4 days is not only a perfect time for exchange ideas and topics on the state of the art in cosmology and gravitation, but also a perfect moment for exchange with each other, especially for grad students. And also, it was the time to meet all our new friends. So we hope you will join us in next edition of this meeting. So once again, thank you very much.
Okay. Yes, you are welcome to the next version of the event in the next year. Yes. Now, maybe some invited speaker can, the dean or the dean also can give some words for us. No problem. Can be in English, in Spanish, in Portuguese. Okay. Okay, but can be in Spanish, decano, no problem.
Okay.
Yes.
Buenas tardes. Quiero agradecer la presencia de todos ustedes. Qué lindo que hayan podido venir a Arica. Muchas gracias por darse la molestia. Es muy difícil llegar a Arica considerando que somos una región extrema. Por lo tanto, este evento, que ha sido para mi gusto todo un éxito, marca una diferencia entre lo que hacíamos antes y lo que estamos haciendo ahora, con todo el apoyo a nuestros posgrados, a nuestros estudiantes y, bueno, a toda la comunidad. Muchísimas gracias, bienvenidos, y los esperamos nuevamente en Arica lo antes posible. Y de paso les digo que hay un rico café afuera.
Ok. Sara, puedes venir también para que... bueno, también la secretaria, el secretario of the event, Sara. Sí. De personal técnico también. Gracias. Now, I would like to say to you, you are welcome to the dinner in the night. Yes, it's going to be 7:30. Yes, and also it's going to be covered by the organizing committee. Okay. Let's go to a coffee break, to the cocktail, ending cocktail. Okay.